In 1943, a year marked by the turmoil and challenges of World War II, the Nobel Prize in Physics was not awarded. This decision, taken amidst one of the most turbulent periods in modern history, reflects the impact global events can have on the realms of science and academia. In 1944, the Nobel Prize in Physics was awarded to Isidor Isaac Rabi, an American physicist, for his revolutionary development of the resonance method for recording the magnetic properties of atomic nuclei. Rabi's work was a milestone in the field of quantum mechanics and atomic theory. He discovered a method to measure the magnetic properties of atomic nuclei using a technique now known as nuclear magnetic resonance (NMR). This method involves aligning atomic nuclei in a magnetic field, and then disturbing this alignment with a specific radio frequency. By measuring the response of the nuclei, Rabi was able to deduce their magnetic properties with unprecedented precision. Rabi's discovery had profound implications in fundamental physics, particularly in understanding the quantum behavior of atoms and molecules. His techniques allowed for more accurate measurements of magnetic moments and quantum spin dynamics, offering deeper insights into the structure and behavior of atoms. This contributed significantly to the theoretical framework of quantum mechanics, enhancing our understanding of the fundamental principles governing the microscopic world. Beyond its theoretical importance, Rabi's work paved the way for practical applications, most notably in the development of magnetic resonance imaging, MRI technology. MRI has become a critical tool in medical diagnostics, providing detailed images of the body's internal structures without the use of ionizing radiation, as in X-rays or CT scans. It works on principles similar to Rabi's discoveries, where radio frequency pulses are used to manipulate the alignment of hydrogen nuclei in water molecules within the body, and their subsequent relaxation and emitted energy are measured to create detailed images. Furthermore, nuclear magnetic resonance, stemming from Rabi's research, has also become an essential tool in chemistry and biochemistry for the analysis of molecular structures, dynamics, and interactions. It enables the detailed study of proteins, nucleic acids, and other complex molecules, playing a crucial role in drug discovery and the understanding of biochemical processes. In 1945, the Nobel Prize in Physics was awarded to Wolfgang Pauli, an Austrian-born physicist, for his discovery of the Pauli exclusion principle, a fundamental principle of quantum mechanics. Pauli's principle, formulated in 1925, revolutionized the understanding of the structure of matter at the atomic and subatomic levels. The Pauli exclusion principle states that no two electrons in an atom can have identical sets of quantum numbers, effectively meaning that no two electrons can occupy the same quantum state simultaneously. This principle has far-reaching implications in physics and chemistry. It explains a wide range of physical phenomena, from the structure of the periodic table to the stability and properties of atoms. Pauli's principle helps to explain why atoms have distinct layers of electrons, electron shells, and why elements exhibit specific chemical behaviors. It is key to understanding the electronic configurations of atoms, which in turn dictate how atoms bond and form molecules. In addition to its fundamental role in quantum mechanics, the Pauli exclusion principle is also crucial in astrophysics, particularly in the study of white dwarf stars and neutron stars. In white dwarfs, it is the pressure arising from the exclusion principle, known as degeneracy pressure, that prevents these stars from collapsing under their own gravity. Similarly, in neutron stars, the Pauli exclusion principle applied to neutrons instead of electrons provides the pressure that counteracts gravitational collapse. Pauli's discovery not only provided profound insights into the fundamental nature of matter, but also contributed to the development of quantum field theory and particle physics. It remains a cornerstone of modern physics, underlying much of our current understanding of the physical universe. In 1946, the Nobel Prize in Physics was awarded to Percy Bridgman for his invention of an apparatus to produce extremely high pressures, and for the discoveries he made therein concerning phenomena in this range. Bridgman's pioneering work in high-pressure physics significantly advanced the understanding of the properties of materials under extreme conditions. Bridgman developed techniques and equipment that could generate pressures up to 100,000 atmospheres. This was an extraordinary achievement for the time and opened up new frontiers in physical science. His research under these extreme conditions led to a deeper understanding of phase transitions, the changes that occur when materials switch between states like solid, liquid, and gas. He discovered numerous new phenomena and properties of materials, including changes in electrical conductivity and the transformation of certain materials into more compact forms. One of the notable aspects of Bridgman's work was his meticulous and innovative approach to problem solving. He not only developed new physical theories but also designed and built the experimental apparatus required to test these theories, displaying a remarkable combination of theoretical insight and practical skill. Bridgman's work often involved studying materials under extreme conditions, such as high pressures and low temperatures. His experiments pushed the boundaries of what was previously thought possible, and his findings had significant implications for various fields of science and engineering. In addition to his scientific contributions, Bridgman was also a dedicated teacher and mentor. He inspired countless students with his passion for knowledge and his commitment to pushing the boundaries of human understanding. Throughout his career, Bridgman received numerous accolades and honors for his groundbreaking work. He was awarded the Nobel Prize in Physics in 1946 for his discoveries in the field of high-pressure physics. Despite his many achievements, Bridgman remained humble and down-to-earth. He was known for his kindness and generosity, always willing to help others and share his knowledge. Bridgman's legacy continues to inspire and influence scientists and researchers today. His innovative approach to problem-solving and his dedication to pushing the boundaries of knowledge serve as a reminder of the importance of curiosity and perseverance in the pursuit of scientific discovery. Bridgman's contributions had substantial implications in various fields, including geophysics, where his findings helped in understanding the physical properties of Earth's deep interior. His methods and discoveries also influenced material science, aiding in the development of stronger and more resilient materials. In 1947, the Nobel Prize in Physics was awarded jointly to Sir Edward Victor Appleton for his discoveries in the upper atmosphere, particularly the layer which is named after him as the Appleton layer. Sir Edward Victor Appleton's research significantly contributed to our understanding of the ionosphere, an ionized layer in the Earth's upper atmosphere. His work in the 1920s and 1930s led to the discovery of a layer of the ionosphere, which became known as the Appleton layer. This layer reflects radio waves, enabling long-distance radio communication. Appleton's studies laid the foundation for the development of radar technology, particularly crucial during World War II, and had a profound impact on telecommunications and atmospheric physics. In 1948, the Nobel Prize in Physics was awarded to Patrick Maynard Stuart Blackett for his development of the Wilson cloud chamber method, and his discoveries therewith in the fields of nuclear physics and cosmic radiation. Blackett's work significantly advanced the study of elementary particles and played a crucial role in the field of particle physics. The Wilson cloud chamber, originally invented by Charles Wilson, is a device used to detect and visualize the paths of charged particles. Blackett refined and expanded the use of this instrument, making it a powerful tool for the study of cosmic rays and nuclear reactions. He implemented a method to take photographs of the tracks created by these particles in the cloud chamber, allowing for detailed analysis of their properties and interactions. One of Blackett's notable achievements was his experimental proof of the creation and annihilation of particles, providing evidence for the existence of positrons, the antiparticle of electrons, in cosmic rays. His research also contributed to the understanding of the processes of nuclear transformations, including the disintegration of nitrogen nuclei by alpha particles and the creation of other elements, a process known as nuclear transmutation. Blackett's work in cosmic ray research also led to significant discoveries about the nature of primary cosmic rays and the interactions between high-energy particles and matter. His studies provided insights into the fundamental forces and particles that constitute the universe, contributing to the broader understanding of particle physics. The awarding of the Nobel Prize to Blackett in 1948 recognized his innovative contributions to the development of experimental methods in physics, and his profound discoveries in the fields of nuclear physics and cosmic radiation. His work not only deepened the understanding of atomic and subatomic processes, but also laid the groundwork for future research in particle physics and astrophysics. In 1949, the Nobel Prize in Physics was awarded to Hideki Yukawa for his prediction of the existence of mesons on the basis of theoretical work on nuclear forces. Yukawa's groundbreaking work, conducted in the late 1930s, marked a significant milestone in theoretical physics and greatly contributed to the understanding of the fundamental forces in nature. Yukawa's theory was developed to explain the strong nuclear force, which is the force that holds the nuclei of atoms together. Prior to Yukawa's work, the nature of this force was not well understood. Yukawa proposed the existence of a new particle, which he initially called a meson, meaning middle particle in Greek, to mediate this strong force between protons and neutrons in the nucleus. According to his theory, these mesons would be heavier than electrons but lighter than protons and neutrons. The real breakthrough came when Yukawa's theoretical particle was experimentally confirmed. In 1937, a particle with the properties predicted by Yukawa was discovered in cosmic rays, providing strong evidence for his theory. This particle, initially called the muon, was later understood to be a different type of particle, but the discovery of the pion, p-meson, in 1947 fully corroborated Yukawa's prediction and theory. Yukawa's work was instrumental in the development of quantum field theory and the model of strong interactions, known as quantum chromodynamics. His meson theory laid the groundwork for subsequent developments in particle physics, including the study of various types of mesons and the exploration of the fundamental forces that govern the behavior of subatomic particles. The awarding of the Nobel Prize to Yukawa in 1949 recognized his significant contributions to theoretical physics and the impact his work had on the understanding of atomic nuclei and the forces that bind them together. It highlighted the importance of theoretical predictions in advancing scientific knowledge and paved the way for further discoveries in the realm of particle physics. In 1950, the Nobel Prize in Physics was not awarded. The prize money was allocated to the special fund of this prize section. There have been several instances where the Nobel Prize in Physics was not awarded in a given year. According to the statutes of the Nobel Foundation, if no work is found to be of the importance indicated in the will of Alfred Nobel, the prize may be reserved until the following year. In 1951, the Nobel Prize in Physics was awarded jointly to Sir John Douglas Cockcroft and Ernest Thomas Sinton Walton for their pioneering work on the transmutation of atomic nuclei by artificially accelerated atomic particles. Their groundbreaking experiments in the early 1930s led to the first successful splitting of the atom, marking a significant advancement in nuclear physics. Cockcroft and Walton's achievement was accomplished at the University of Cambridge's Cavendish Laboratory. They built an apparatus known as a Cockcroft-Walton generator, which was used to accelerate protons to high energies using a high-voltage machine. In 1932, they directed these high-speed protons onto lithium atoms, successfully splitting the lithium nuclei into alpha particles. This was the first time atomic nuclei had been artificially disintegrated and served as direct proof of Einstein's equation E=mc2, demonstrating that energy could be released through the splitting of atoms. Their experiment not only confirmed theories about atomic structure and the immense energy locked within the atom, but also opened up a new field of research in nuclear physics. This research had profound implications, leading to the development of nuclear power and laying the groundwork for the discovery of the neutron by James Chadwick in the same year. Furthermore, the techniques developed by Cockcroft and Walton for accelerating particles laid the foundation for subsequent developments in particle physics, including the construction of more powerful particle accelerators. These accelerators have become essential tools for probing the fundamental structure of matter and the forces that govern the behavior of particles. The awarding of the Nobel Prize to Cockcroft and Walton in 1951 recognized their significant contributions to the field of nuclear physics and the impact of their work on both theoretical and applied aspects of the discipline. Their achievements not only deepened scientific understanding of atomic processes, but also had far-reaching implications for both energy production and the study of the fundamental particles of the universe. In 1952, the Nobel Prize in Physics was awarded jointly to Felix Bloch and Edward Mills Purcell for their development of new methods for nuclear magnetic precision measurements and discoveries in connection therewith. Their groundbreaking work led to the development of nuclear magnetic resonance, NMR spectroscopy, a technique that has since become a fundamental tool in chemistry, physics, and medicine. Felix Bloch and Edward Mills Purcell independently discovered nuclear magnetic resonance in 1946. Their research demonstrated that nuclei in a magnetic field absorb and re-emit electromagnetic radiation, a phenomenon that occurs at a specific resonance frequency, which depends on the strength of the magnetic field and the properties of the isotope of the atoms involved. This discovery opened up new ways to study the atomic nucleus and provided a powerful new tool for molecular analysis. Bloch's and Purcell's techniques involve aligning the magnetic moments of nuclei by placing them in a strong magnetic field, and then disturbing this alignment using a radio frequency pulse. The way in which the nuclei return to their original states, their resonance, reveals detailed information about the molecular structure and dynamics of their environment. NMR spectroscopy, arising from their discoveries, has become a critical method for understanding the structure and properties of molecules, particularly in organic chemistry and biochemistry. It allows scientists to determine the physical and chemical properties of atoms, or the molecules in which they are contained. It is also used in studying molecular physics, crystals, and non-crystalline materials through NMR relaxation, which provides insights into molecular dynamics at the atomic level. In medicine, the same principles are applied in magnetic resonance imaging, MRI, a powerful diagnostic tool that produces detailed images of the inside of the human body without the use of ionizing radiation. This has revolutionized medical diagnostics, allowing for the non-invasive observation of soft tissues with high precision. The awarding of the Nobel Prize to Bloch and Purcell in 1952 recognized the immense scientific and practical importance of their discovery. Their work has had a lasting impact on various scientific disciplines, fundamentally changing the approaches in structural analysis of molecules and medical imaging.